We're now going to study the second part of this chapter, and that has to do with elasticity. What is elasticity, and how does that compare with plasticity? Well, the issue arises when an object is being deformed under the influence, for example, of a force. So after the object is deformed and when the force that causes deformation is gone, how does the system behave? In some cases, the system will try to get back to its original form. In some cases, the deformation stays permanent. And for example, if you look at these two cases, a spring versus a beanbag, you can see clearly that the behavior is going to be very different if I apply a force on each one of them and then I remove that force. For the case of the spring, if you stretch it, the spring gets longer, and if you compress it, the spring gets shorter. Either way, it's a deformation. But once you remove the force that causes the deformation, common sense tells you that the spring will try to get back to its original shape. And in fact, it succeeds in doing that unless the deformation is too much. On the other hand, if you look at a beanbag, the weight of the cat creates a dip, and that deformation is permanent even when the cat is gone. And in the first case, the spring being an example, the system rebounds to the original shape after the deformation is gone. This tendency to keep its original form is called elasticity. Okay, elasticity. So this is what we say an elastic object. On the other hand, if you look at the beanbag, the deformation is permanent. The object does not go back to the original shape, even though the cause of the deformation is gone, and that is called plastic behavior. So these are the two typical examples. Now, let's focus on the case of elasticity. And that is when an object being deformed will rebound to the original shape after the force of deformation is gone. Take a look at this example of the spring again. Initially, the spring is at its what's called natural length. It's neither being compressed nor stretched. And if you compress it, okay, by applying force along the direction of the green arrows, then what happens is that the spring doesn't like it, okay? So it gives your hands a force back like this, right? This force is against the deformation. It tends to push the spring back to its original length. Okay, so it is against the deformation. And similarly, if you take that spring and you stretch it, so the force applied is opposite to the previous case, then the force of the spring is also reversed in direction. So now the spring will tend to give you a force like that. Again, the purpose of this force of the spring is to try to maintain the original length of the spring. It's against the deformation. Okay, so in either case, the force of the spring, the elastic force of the spring has a purpose, and the purpose is to restore the spring to its original length. So it's against deformation. Okay, so we call it restoring force. This is true for any object with elasticity. When you try to deform it, you encounter a resistive force from that object. And the direction of that resistive force is to try to restore the original shape and size of the object. That is called restoring force. All right, how does the restoring force behave? How does that depend on the amount of deformation? Well, there are just countless types of objects with elasticity, but turns out that if you look at a small amount of deformation, okay, so you do not deform the thing a whole lot, just give it a tiny small amount of deformation, then they all have something in common as far as the behavior of restoring force. To understand that, let's imagine we draw a plot of the amount of deformation and the corresponding response. Okay, that is the restoring force. All right. Take a look at the example of a spring. Okay, the deformation, I can use a letter X to denote the deformation. That's amount by which the spring gets longer. Now, when X is positive, we say the spring is stretched. When X is negative, we say the spring is compressed. We all know that if the spring gets stretched by an amount x, then there's a restoring force that is against the direction of the force which you would apply to stretch the spring. So the restoring force is on the negative x direction if I apply a force along the positive direction, which means to stretch the spring. Okay, so the force is negative when the deformation is positive. So that means, the force, of course, the force has to start from 0, right? Because if there's no deformation, then there's no force from the spring. So it starts from this point, right? And it's negative. So when the deformation is positive, so the curve will start from the origin and will extend into the fourth quadrant. It's going to be something like this. Okay. On the other hand, if the deformation is negative, meaning that the spring is compressed, so x is less than 0, then the restoring force is also the opposite, and that is the restoring force try to increase x, increase the length so that the spring is no longer being compressed. So now this time the force is positive. It tends to increase the size, the length of the spring. So now I can also extend this curve back into the second quadrant, and that is when x is negative. Okay, start from 0 and becomes negative. So I'm going to draw something like this. Now, what is the shape of this curve? Well, I don't really know for sure. I mean, this curve can be complicated, in general, it can be complicated if you extend deformation to large values. I mean, if you take an object, if you stretch it, compress it too much, God only knows what's going to happen. It could behave in a weird manner. It can even rupture, right? Can just get broken. But if we're not interested in large deformation, we're only focused on the small amount of deformation right in the middle here. Okay, then the situation becomes easier because look, this curve has to pass through the origin. Okay, there's no question about that, because when there is no deformation, meaning x equal to 0, then responsive force is also equal to 0. So it has to pass through this point of 0, 0. So once again, let me stress that. It has to pass through this point 0, 0. And there has a curve, right? There's a curve. Now this curve can have any shape. Okay. However, if you look at a small part of this curve, only a tiny part of this curve right here, then no matter how complicated this curve is, in general, this small part of the curve resembles what? A straight line. Isn't that true? Resembles a straight line. Okay. And that straight line has a slope, which we know is negative. But if you only look at the magnitude, and then we don't worry about this negative sign, then we write force equals to a constant k times x. Now, if this is a spring, we know what that k is. It's called the spring constant. Okay, so this is the magnitude. F is the magnitude of the responsive force from the elastic object, such as the spring. Okay, x is the deformation I cause for the spring. F is how much force it exerts on my hand to try to fight it back. Okay, that k, in the case of spring, it's called a spring constant. But in the most general case, we're not limited to a spring. I mean, it can be anything. It can be any elastic object, which responds to my hand trying to deform it. Okay, and this x doesn't even have to be a linear deformation. It could be an angular deformation. And this force, it doesn't even really have to be a force necessarily. It could be a torque. Okay, I may have something. I may have a situation where I want to rotate an object from equilibrium, and the object fights back with a restoring torque. That's also possible. So this is a more generalized version of the force and more generalized version of the displacement deformation x. But the point is, for small deformation, you have a linear response from the system. Linear response. That is very important. And it's very general. Again, we're not limited to a spring for small displacement, or for small deformation, I should say. Okay, so the key is small deformation. you get linear response. A very general argument. Okay. Now, question is, what is the K equal to? If I give you a steel rod, for example, I'll give you a steel rod, okay, and I ask you if I stretch the steel rod or compress the steel rod, how much force do I get in return? You know, how much does the steel rod try to fight back, right? And you know, I can draw a picture of this rod. It's got a certain cross-section area, certain length, certain area, right? And if I pull it, I stretch it with a force here, of course, equal amount of force there. So the thing gets longer, right? And so this time delta x, x is actually the length change delta L. Question is, if I apply this general formula here to the case of the steel rod, my question, what is that K equal to? Well, clearly K has to do with material makeup, right? Is it steel or is it rubber band? It's certainly, you know, you apply the same force, you're going to get very different amount of deformation. And secondly, K also depends on the geometrical shape of the rod. How long is it and how thick is it, the area A? These things also matter, right? So in order to understand more details of what K depends on, we have to introduce the concept of what's called elastic modulus, okay, which separates the factors of shape and size, such geometrical factors, from the material makeup of this elastic system. Okay, so we isolate, we take out only the factor that depends on the material makeup. And we have a quantity called elastic modulus. Depending on what kind of deformation you have, there are different types of elastic modulus. So let's take a look at the three most commonly defined elastic modulus. The first one, the so-called Young's modulus, is for linear displacement or linear deformation. Okay, so this is a diagram from the textbook. So you have a, an object which is shaped like mostly shaped like a rod. Okay, it's got a length L initial. Sometimes we just call it L. It doesn't really matter. And it's got a cross-sectional area A. Now, suppose I fix one end using this clamp, and I apply a force F to stretch the rod. How much is the deformation delta L? How much longer does it get? That's what I want to know, right? All right, we know delta L is going to be linearly proportional to F. That's the most general observation for, at least for small delta L. That's what we expect, right? So we expect delta L to be proportional to F, okay? But what is that constant of proportionality? What's that K equal to? Well, let's see here. Let's take a closer look. Let's see what delta L depends on, okay? Delta L certainly depends on F, okay? So it's a linear function of F, but I leave some space here before F to add that constant in. Now, so what's also important? What also determines delta L? Well, first of all, do you think the length L matters? So what if I double the length? I keep everything the same, it's the same type of rod, made of same material, same cross-sectional area, except it's twice as long. Now, if I apply the same force F to pull this rod that is twice as long, do I get the same delta L? I don't. Because when you pull a rod that's twice as long, okay, so here's a rod of delta L, here, I'm sorry, L, then you have, this is L, this is also L. So when you have a rod that's twice as long, you can think of this rod as made of two identical rods, end to end, each of length L. Now, if you fix this end, okay, and you pull along the other end, then each of these rods will experience a force F, don't you think? And therefore, each of these two half rods will extend by an amount delta L, right? Then now, what is the total amount of stretch? Isn't that 2 delta L? See? So when you double L, you also double delta L. Therefore, delta L is proportional to L. Okay, there's an L here as well. All right? There's an L here as well. What about the cross-section area? A. How does that matter? Well, common sense tells you that the thicker the rod is, the stronger. Therefore, when you increase A, you're going to decrease delta L for the same amount of force applied. Now, how does it actually depend on the cross-section area A? That's actually quite simple to understand as well. Suppose you have a rod L, okay? And I double its cross-section area, keeping the length the same, everything else the same. This is the same as putting two identical rods next to each other like this, okay? So you glue them together like this, and you apply the same force F, okay, while keeping the other end fixed. Now, you only have one force F, but this force is now applied evenly across an area, a cross-section area twice as large. That is the same as saying that you're giving each half of the rod only half of the force, don't you think? Okay, now when you apply half of the force to this rod, you're gonna get only half the stretch. Okay, so therefore doubling the cross-section area is the same as using the same force to pull on two identical rods side by side. So each rod gets only half force, and therefore you get half the stretch. Okay, so A doubles delta L is half. So delta L is inversely proportional to A. Does that make sense? Okay, so this is how delta L depends on the geometry of the rod, the length, and the cross-section area, and also the force. But of course, what also matters is what kind of material the rod is made of, right? So there has to be a constant which is determined by the material makeup. There's a constant here in front of it. I'm going to put it in this parenthesis. Now clearly, the smaller that constant, the smaller delta L for the same force, and therefore the stronger the material. Okay, now suppose I introduce a parameter, a constant, which gets greater when the material is stronger. Okay, and then I'm going to put that constant here. I'm going to call that constant y, but I'm not going to put a y just like this, because that would mean if y is greater, then delta L is also longer, and therefore the material is actually weaker, don't you think? A weaker material stretches more, right? So no, I'm not going to put y here. I'm going to put this as 1 over y, okay, for that reason. I'm going to add a 1 over y here. And this parameter y depends on the material makeup, and the greater the y value, the smaller the delta L for, you know, the same force and same physical size, therefore the stronger the material. Okay, and I can then calculate, I can solve for y here. So I get y equals what? Y equals F over A divided by delta L over L. So you see, it's not just the force that matters, it's force per unit area. Okay, if you take the same force, you spread over a large cross-section area, you don't get much stretch. So it's F over A that's really important. And this is called stress. F over A is called stress. Okay, on the other hand, it's not just delta L, it's delta L over L that really matters. Because look, if you take a rod that is very long, okay, and let's say the rod is, you know, 2 miles long. I mean, it's hard to imagine, but suppose you get something that long. Does it really matter if it gets longer by like a millimeter? It's hardly noticeable, right? But look, if the rod is only 2 millimeters long, extremely short one, you stretch by a millimeter. Wow, that's a 50% increase in length. Of course, it's not going to be happy, right? It's much harder to do. So it's not delta L, it's the fractional change. It's the percent change in length that matters. And delta L over L is called strain. Okay, so when you apply a stress to the material, you're going to cause a strain. Okay, F over A is the stress that causes a strain of delta L over L. And the ratio of stress over strain is called the Young's modulus. That is the definition of the so-called Young's modulus. Again, what does a large value of Young's modulus tell you? It tells you that everything else being the same, you don't cause a lot of deformation, which means material is strong under the same force because it doesn't stretch as much. Okay, what is the SI unit of Young's modulus. It's force over area divided by delta L over L. You know, delta L over L, delta L and L have the same unit, so there is no unit in the denominator. Therefore, the unit of Y in SI system is just force over area, or Newton per meter squared. Okay, Newton per meter squared. And Newton per meter squared has another name. We call it Pascal, after the French physicist Pascal. Why did he get the honor? You will see that when we study the concept of pressure in a later chapter. Okay, so what is 1 Pascal? It's you apply 1 Newton of force over an area of 1 meter squared. So 1 Newton per meter squared here. That's called 1 Pascal. Okay, so it's not a whole lot of stress, because 1 Newton is not a big amount of force, and you stretch it over an entire square meter, so that's not much. So Pascal is a rather small unit. All right, so that's the so-called Young's modulus. It has to do with linear deformation. Now, what's shear modulus? Another commonly used definition of modulus. This time, you don't have a linear deformation. You don't make it longer or shorter. Rather, you cause a sidewise deformation. So, for example, in this case, you can see in this diagram, we have this box, right? We have this box, or you can think of it as just a block of material. We fix its bottom face. Okay, we fix its bottom face. So this face is glued to the table. And then what we're going to do is we're going to apply a sidewise force, F, on the top surface. Okay, we apply force like this. No, we don't compress it or stretch it. Rather, we just apply a force to pull the top side to the right. Of course, automatically the table is going to give it a reactive force like this. So the net force on this box is still 0. The box is not going anywhere. Okay. Now, that is going to cause a deformation, so that the side surface is no longer a rectangle, but rather the top surface is now shifted this way, right? The bottom surface stays the same because it's glued. So the top surface, this point moves forward by an amount delta x. Okay, question is, what is delta x equal to? Okay, so what is delta x? You know it's proportional, it's going to be proportional to F. That's always, this linear dependence is always true for small amount of deformation. It's proportional to F, okay? But what is the constant of proportionality? Well, the constant depends on the geometry. It also depends on the material makeup, right? Just as we saw in the case of Young's modulus. How does it depend on the geometry? Well, the height of the box matters. Because look, if the box is very, very tall, then I can basically extend this square or this rectangle like this, right? It becomes tall. So clearly, delta x becomes greater. It increases linearly, proportional, right? So therefore, we know it's proportional to the height h. That matters. What else? Well, the other thing that matters is you apply the force F over a cross-section area, right? Over a cross-section area. Now, clearly, if the cross-sectional area is small, then you have a greater concentration of the force, and you're going to cause a greater amount of deformation delta x. Suppose you double the area, and that is using the same argument as we saw in the Young's modulus. You are basically applying only half the force to each area. Therefore, you're going to get half the deformation. So delta x is going to be inversely proportional to area, just like the case of Young's modulus. And just like the case of Young's modulus, there's a constant in front of it, and that constant determines eventually how much delta x is, and it in turn is determined by the material makeup of this box. And just like the case of Young's modulus, when I introduce a modulus here, the so-called shear modulus, I'm going to define the shear modulus such that the greater the shear modulus, the stronger the material against shear deformation. Therefore, the smaller delta x is, the greater this constant, this modulus. So I'm not going to put an S here, because just like the Young's modulus, if you put an S here, then the greater the S, the greater the delta x, suggesting the weaker the material is. We don't want that, so I'm going to put it at 1 over S, just like the case of the Young's modulus. Okay, and guess what S is called? Yeah, it's called shear modulus. So S is defined as what? You can solve for that. Okay, so it is delta x over h. I'm sorry, that's in the denominator. Delta x over h, and then F over A. Again, it's stress over strain. Okay, it's still stress over strain. Except the definition of the strain in this case is a little different. H is how tall this box is, and delta x is how much the top surface is shifted perpendicularly to the height. So it's a sidewise deformation. Okay, so that's called shear modulus. And the unit is the same as the Young's modulus in Pascal. Now the bulk modulus, that is for three-dimensional deformation. Okay, when you put something in a fluid, okay, the fluid exerts a force in all directions on that object, and that will make it smaller. That will compress it. How much smaller does the volume get? That has to do with so-called bulk modulus. Okay, so we're going to follow the same idea. This time, it's the volume that we have to consider. Okay, so delta V. The things get smaller when you put it under a certain amount of pressure. So you have delta V. What is delta V equal to? Well, delta V has to do with the amount of force that you apply. Okay, has to do with proportional to the amount of force you apply, just like before. Right? But what else does it depend on? Do you think the volume matters? Yeah, of course the volume matters, because again, when you double the volume, then you're using the same force to compress twice as much material. Then each half only gets half the force, and therefore, you're going to get half of the deformation. So it has to do with the volume. It's proportional to volume. When you get greater volume, you get greater delta V. Okay. What else? What else matters? Well, it also has to do with the surface area, don't you think? Because when you apply the same area, when you apply the same force over a smaller area, you're going to get greater response. So therefore, when you double the area, you have diluted the effect of the force by half, and delta V will correspondingly drop to 1/2. So you can imagine it's also inversely proportional to surface area. Okay, and following the same logic, we're going to add a constant in front of it. That constant will be 1 over a modulus here, and the greater this modulus, the smaller this overall constant in the parentheses, and therefore the less the amount of deformation, therefore the stronger the material. And this constant is called the bulk modulus, B. Okay, so we solve for B. B is then equal to F over A divided by delta V over V. Now, there is one thing I need to stress. If you think of F only as the magnitude of the force with no sense of direction, I mean, it's going to be a compressive force anyways, then delta V is going to be negative when you apply a force, right? I mean, the thing only gets smaller when you try to compress it. It doesn't get any bigger. But everything else is the same. Everything else is positive, and F is only the magnitude of the compressive force. So if you keep a definition like this, V is going to be negative, because delta V is the only negative quantity. Everything else on the right-hand side of the equation is positive. You don't want that, so therefore you're going to attach a negative sign to the definition of B here. Okay, so you add a negative sign. It's very important. This will keep B as a positive quantity. Okay, so that is so-called bulk modulus. The bulk modulus is important when it comes to compression of an object surrounded by a fluid. You will see that in later chapters. So again, these are the three commonly used examples, commonly defined quantities of modulus. They have to do with how strong the material is. In general, the greater these moduli, the stronger the material is against deformation. An example of Young's modulus for steel, okay, for steel is 200 GPa. What does G mean? So Y equals to steel 200 GPa times G is 10 to the positive 9, okay, Pascal. That sounds like a big number, right? 2 times 10 to the 11 Pascal. But what exactly does that mean? Well, let's put it to some numerical calculation. Let's see what kind of deformation a steel rod, a typical steel rod will get if I apply a typical force, okay? So imagine I have a steel cable, right? A steel cable, and it's got a certain length, a certain cross-section area. So I'm gonna put a length, okay? I'm gonna draw a steel cable, okay? The length of this cable is 1 meter, right? 1 meter. So it's a typical length, 1 meter. And of course, the cross-section area also matters. I'm going to imagine this is a 1 millimeter by 1 meter cable. It's actually, you know, you hardly see any square cables. So this should be some sort of circular shape, but it doesn't really matter. We just estimate roughly, okay? So the cross-section area is roughly 1 millimeter by 1 millimeter. So it's a rather thin cable. It's not a very thick one. Okay, 1 millimeter is 10 to the negative 3 meters. So this is 10 to the negative 6 meters squared. Okay, meters squared. Don't forget that squared here. And if we apply if we suspend a weight under this cable, okay, so this cable is this is the ceiling. Now I'm gonna pull it with a weight. This weight is 100 pounds. It's quite a lot actually, okay. 100 pounds. Okay, so I suspend a 100-pound load under this cable. Question is, how much will the cable stretch as a result? Well, I'm just looking for delta L, right? The length of the cable L is 1 meter, right? The definition of Young's modulus, FA over delta L divided by L. So you can solve for delta L. You can solve for delta L. In fact, we got delta L in the beginning, right? We got delta L right here, you know, this delta L, okay? So then we, you know, it's the same formula that we use here. We plug in the numbers. Length L is 1 meter. The Young's modulus, 200 times 10 to the positive 9. F is 500 newtons. Remember, I have to use SI units. Okay, I have to use prime SI units. I cannot use pounds and mix it with, you know, millimeters and meters and so forth. Okay, so roughly speaking, as you know, 1 pound is about 5 newtons. Okay, or more precisely, 9.8 newtons is equivalent to 2.2 pounds, but you know, roughly 1 pound for 5 newtons. So 100 pounds is roughly 500 newtons. Just, it shouldn't be too far. Okay, divided by the area of the cross section, 10 to the negative 6. If you do the math, you get 2.5 millimeters. 2.5 millimeters. Okay, so you know that makes sense. You know, a steel cable will stretch. Okay, the amount of stretch is 2.5 millimeters for a 1 meter long cable, pretty thin, like a millimeter in thickness, and I put a 500 Newton or 100 pound weight on it. It's going to stretch, yeah. By how much? By, you know, a little over 2 millimeters. So it's noticeable, but it's not that large. That makes sense. Okay. And you can think of many other examples of that. And more importantly, when you calculate this, when you're given, you know, the load and the physical size, you can calculate the amount of strain, stress, which is the force applied to this rod divided by the area. And you can compare that with the so-called ultimate strength of this material. If you don't want this thing to break, the stress that you apply better stay way below the ultimate strength, because it's going to break at that strength. Even long before that happens, it's going to start to deform plastically, which means the deformation will no longer be temporary, because it stretches too much, it doesn't want to go back anymore, even after you remove the deformation. Okay, here is a more general diagram for the behavior of in the elastic system when you give it a large amount of deformation. Okay, we are focused mostly here in this area, in this area. Okay, let me label it. It's called linear regime, where the stress is small and the corresponding strain is also small. Okay, but when you stretch it a lot more, then it's going to stay linear for a while, depending on what material it is. Some materials have a large linear regime, some have a rather narrow one. But at some point, it's going to go beyond. It's going to break from the linear regime. Something happens, and this is called ultimate stress, ultimate strength, and that is the strongest. This is the greatest amount of stress the thing can possibly withstand. If you pull it even harder, it's actually going to give you less stress. It's going to withstand less stress. At some point, you pull it too hard, it's going to fracture. It will be broken. Okay, I'm not going to get too far into details of the shape. Again, we're more interested in this region. Okay, the linear region. And you can see clearly in the linear region, the stress and strain, there's a linear relationship between them. And again, that is a very general argument based on the shape of a curve near the origin. If it passes through the origin, it's got to be linear. Okay, so that is our first lecture for elasticity. And then in the next lecture, we're going to look at a practical, interesting example about the compression caused by the weight of the Washington Monument at its base.